So here's a quick little review of HOMO LUMO. So all of this is from chapter 1, and a little bit is sprinkled throughout the rest of the book, but here's the main gist of it. So when two atoms, so when two atoms come together like hydrogen and they form a bond, each hydrogen has one electron in its 1s shell, and that one electron in each shell comes together, combines to make a bond. But what is actually going on? So these atomic orbitals are merging together, and when they merge together, it lowers in energy to form this bond. So you have this hydrogen being merged together, but kind of from a molecular state, what's going on. So let's kind of rethink about something that you learned in Gen Chem. Remember that we said energy is conserved, orbitals are conserved, so you can't lose orbitals. So if hydrogen has one atomic orbital each, so that means there's 2 atomic orbitals total. When they combine, you should get 2 molecular orbitals. So what are these molecular orbitals? Well, one of them is very obviously when the hydrogen's electrons come together, they form a bond, and you have the pairing of the electrons. So when we have the pairing of electrons, that drops the energy of the atomic orbital. When they merge together, it gets those molecular orbitals. So when we're talking about energy, it's even lower than the atomic orbitals originally were, which is why bonding happens. It's a more stabilizing effect. But then what is the other one? There's no more electrons. So the other one is a molecular orbital which has no electrons in it. It's going to be higher in energy, and we can give these things some terms. But before we do that, let's kind of draw what it kind of looks like. So when the 2 atomic orbitals, the s orbitals, overlap, they're going to merge kind of into one atomic orbital. That the 2 phases of the s orbital overlap. So you take the 2 s's and they overlap in phase. And when they overlap in phase, that's favorable. But what about the other molecular orbital? That's when the orbitals overlap out of phase, so there's going to be a node. And nodes increase the energy of the orbital. Now, there's no electrons in there, so it's not a problem because there's no electrons in there. But when we're talking about hydrogen, we have 2 molecular orbitals, and we give them some names. So the ones that are filled are called bonding because there are electrons in their bonding molecular orbitals. We'll see at another point there's another one that can happen, but we learned that in Unit 3. And then we have anti-bonding. Because this is a sigma bond, we can also call this sigma star and just call this sigma bonding. But notice I wrote the word HOMO here. HOMO, remember from chapter 1, means highest occupied molecular orbital. Well, it's the only molecular orbital and it has electrons, so it's occupied. And the other one is LUMO. Now, none of this really makes any difference whether they're HOMO and LUMO, because lowest versus highest, well, one is unoccupied, one is occupied. But when we start thinking about more complicated molecules that have lots of molecular orbitals in them, and let me give you an example. This is just a hypothetical molecule that, let's say, has, let's say we had 8 atomic orbitals overlapping to form 8 molecular orbitals, and each atomic orbital had 1 electron apiece. So I would fill my molecular orbitals. Don't worry about what exactly the energies are or where they are in relationship to each other. That's not in the scope of what we're going to talk about. But let's say that they were a linear arrangement and each successive one is higher. So the top, so I'm going to pretend that these are sigma bonding, right? So these are sigma bonding molecular orbitals. And if I wanted to designate the HOMO, this is the HOMO. It's the highest occupied molecular orbital. Now that one makes more sense because there's other molecular orbitals, but in the hydrogen there was only one, so it is the highest. And then of the sigma star molecular orbitals, or the antibonding, this would be the LUMO. Now who cares? Well, we care because everything you've been doing so far in terms of reactions actually just boils down to HOMO and LUMO. So whenever you're doing a reaction, so let's pretend you have a molecular orbital diagram, energy diagram, and we are talking about reactions happening. So reactions, as we know it, are electron flow. So we are moving two electrons. So we're going to be moving the easiest two electrons that can be moved from the nucleophile to the electrophile that lacks electrons. So how does that relate to HOMO LUMO? Well, let's think very carefully about what we see about these energy diagrams. The HOMO has electrons and the LUMOs do not, right? So LUMOs could potentially accept electrons, HOMOs can. So why specifically those orbitals? Well, the HOMO is the highest occupied molecular orbital, meaning that it's the more energy in terms of, it has the highest energy, let's say highest, not more, highest energy. So it's the more reactive, and because it's more reactive, that means it is the nucleophilic orbital. Okay, so when you think HOMO, we think nucleophile. On the other hand, if you had, and so it's the same diagram that I drew, I just wanted to write HOMO and LUMO separately. So if you want to accept electrons, you want to accept electrons into an empty orbital. So we accept electrons into empty orbitals, but if that empty orbital is higher and higher and higher in energy, it's going to be harder to accept. So the lower the empty orbital, the easier it is to accept electrons from the nucleophile. And we just learned from the, basically it's coming from the HOMO, okay? So if I want to be able to put electrons into the LUMO, I want the lower of, or if I want to put electrons into a molecule, so into one of the antibonding orbitals, I want the lower one, the one that's easiest. So it's easier to get electrons in there, because the higher an orbital is, the more energy it's going to take to put electrons in there. So let me give you another example. Let's say we had these fictitious molecules, and I'm drawing the energy diagrams for them. And let's just pretend that this was coming from our nucleophile. And if you don't remember how to identify strengths of nucleophiles, please check out chapter 6 and chapter 7. Since we won't be reviewing those specifically in class, that's something that I strongly recommend that you look back at. So let's say you had your HOMO and you wanted to put those electrons from the HOMO into the LUMO of the electrophile. So remember, it's two different molecules, right? So if I'm trying to share, I'm not exciting electrons. That's a completely different thing that you're doing. It's a similar concept, but it's on the same molecule. Here I'm sharing electrons between two molecules, and even though this is not exactly how this happens, there's no arrow, but I'm using a mechanism arrow to demonstrate that our electrons, our two electrons, start from the HOMO and go to the LUMO. But if I had something that I had the, again, I'm going to draw an energy diagram. And if this is my nucleophile, and I have my electrophile, if my HOMO were to distribute electrons into the LUMO of the electrophile, as the LUMO gets higher and higher in energy as compared to where the HOMO is, it's going to become harder. So in this example, I'm going to call this example A. It's easier to share electrons, so my nucleophile can better react with the electrophile. And here, even though they can react, the nucleophile is going to have a harder time. So here are some examples of things that might make a HOMO or a LUMO higher or lower. So if your nucleophile is stronger, I would expect, because that means that the molecule is more unstable, because if your nucleophile is stronger, it's going to be more reactive, meaning it's more unstable. I would expect your HOMO's energy to be higher. If I had something that was a better electrophile, I would expect that the LUMO's energy would be lower. So things like carbocations, or over here things like Grignards, or LAH, or any strong nucleophile like a lithium group.